Hello friends, this is Suraj Patil and today we are going to discuss the theorems of functional analysis which are in syllabus of Dr. Babasaheb Ambedkar Mathwade University post graduation program for the first year first semester. So we are going to start with the second unit. So we are going to discuss the first theorem. So we denote it by theorem number 2.1. What it says that let n and n dash be a norm linear spaces and this t from n to n dash is a linear transformation. Then the following conditions on this linear transformation t are all equivalent. So what is the statement's equivalent means? We know that if the one statement holds, automatically other three statements are true, or any of the statement between this four statement or the whatever number of the statements is given, one holds, the other statement automatically will be the true. So the first statement says that this t is continuous. So continuous means it is continuous at each point. The second statement is t is continuous at origin. So what does mean by origin? This origins means nothing but this zero of this n, the zero of this norm linear space n. So third, there exists a real number which is the non-negative real number, that is k is greater than or equal to 0. So with the property, so what is this property? That norm of this t of x is less than or equal to k into norm x for each this x belongs to this space n. And the last one is fourth, if we denote this set x as those x belongs to n such that the norm of x is less than or equal to 1, that is this is a closed unit place, is the what we call as this s is this closed unit pair in n, then its image, what we have to show that then its image, it is denoted by t of s is bounded set in n dash. So we know that what it mean by bounded, the norm should be less than some non-negative quantity. So we have to show that t of s is bounded. So how we are going to show this first statement at equivalent? That we are going to prove 1 is equivalent to 2, 2 is equivalent to 3, 3 is equivalent to 4, and this statement 4 is equivalent to this 3 is equivalent to 4 will be enough. So we are going to start with this for proof. So how we are going to show that this proof is, so we will show that 1 is equivalent to this 2. So first we suppose that if we are going to show that if t is continuous, we suppose t is continuous, then we have to show that this t is continuous at origin. Automatically it will be held by definition, as t is continuous, it means it will be continuous at origin. Then t is continuous at origin, and hence what will get, 1 will imply 2. So we are going to show now reverse implication, 2 implies 1. So conversely, so we suppose, what we suppose, t is continuous at origin. So we have to show that what is target. So target is to prove that t is continuous. So now we know the sequential property for the continuity. Let we suppose that this xn be the sequence which converges to x. So if we show that this t of xn converges to t of x, then this linear transformation t will be continuous at the point x, and since x was arbitrary, then it is obvious that t is going to be continuous everywhere. So xn converges to x, what it implies that this xn minus x will tends to this 0. Okay, it is obvious by definition. So as t is continuous at origin and this xn minus x converges to 0, so obviously this image of this xn minus x will be is going to converge to t of 0. Okay, so this image is going to converge, t of xn minus x is going to converge to t of 0, so which is equal to 0. Okay. So how it is? By since t is continuous at origin. Okay, so t of xn minus x can be written as, this is t of xn minus t of x will converges to 0. So what will imply that this t of xn will converges to this t of x. Okay, and hence what it shows that t is continuous at this point x. Okay, so x was arbitrary, therefore we can say that t is continuous everywhere. So now we are going to show two if and only if 3. So how we are going to show that? So first we suppose that 2 holds. First suppose the statement 2 holds. So what is this statement 2? So we are going to show that this target is to prove that 3 holds. Okay, so we suppose on contrary. So we are going to prove the theorem by contradiction. Suppose on contradiction or contrary that 3 doesn't hold. Okay. So what is 3 says that there exists a non-negative real number with the property norm of t of x is less than or equal to k into norm x for each x belongs to n. Hence it doesn't hold means for each, what it means that then for each natural number, okay, we are going to get the xn in n such that this norm of txn should be strictly greater than n into norm of x. Okay, then with the help of this we define this new sequence, that is yn by xn upon n into norm of xn. Then what will get that this as we know that this norm of t of xn is greater than n into norm of xn. Okay, so if we this quantity we take on this left hand side, then it will implies that this norm of, and we if we take these two terms in one denominator and numerator, then we are going to get this n into norm of xn. Okay, this will be what it will remain on the right hand side, this will be 1. Okay, so that, and this quantity is nothing but this yn. So we are going to get that this t of yn will be, this norm of this t of yn will be strictly greater than n for each natural number. Okay, yes, and further what we can say that this further this norm of yn, okay, so which is equal to 1 by n. So if we take this norm of this quantity, so only xn will get cancelled and 1 by n will remain, and this will tends to 0. This sequence will tends to 0 as this n tending to the infinity, obviously. So what we have to get that sequence yn in n. Thus we have this sequence, this yn in n such that this yn is converging to 0, but this t of yn is strictly greater than 1, so it will not converge to 0. Yes, so what we get that thus we have a sequence which is denoted by yn in this non-linear space n, okay, such that this sequence yn is converging to 0, but this image of this sequence t of yn will not converge to 0, since every quantity t of yn is strictly greater than 1. Sorry, norm of this quantity is strictly greater than 1. So obviously, which is a contradiction? So which is a contradiction? 2, 3. Okay, so it is contradiction, since we know that this it is a continuous at 0, t is continuous at 2. Sorry, it is contradiction to 2, since t is continuous at 0, so t of yn should be converges to 0. So why this contradiction is happening? Because our wrong assumptions. Hence this 3 must be hold. Hence this 3 must hold. Okay, so now we have proved that 2 implies 3. Now we are going to show that 3 implies 4. So we are going to show that, suppose conversely, okay, sorry, so conversely, suppose this 3 holds. Okay, that is there exists a, that is what we say, that there exists a non-negative real number case such that this norm of this t of x will be less than or equal to k into norm of x for every x belongs to n. So we give the number Roman 1. So our target is to prove that, but we have to prove that t is continuous at origin. Okay, so let suppose that this xn sequence be any sequence, arbitrary sequence in n that converges to origin, means 0, origin in n. Okay, that is what we can say, that is this xn is converges to 0. Then by 1 what we can say, that then by 1 we get for each n belongs to the natural number, obviously the norm of t of xn for this sequence, this property will hold by 1. This will be less than k into norm of xn. Okay, so this is we have written this quantity by this property number first for this xn, and as this xn is going to converge to 0, this norm of xn will tends to 0 as n tends to infinity. Okay, since why we have written this xn converges to 0, so thus norm of t of xn, this sequence will converges to 0. So the norm of t of xn is going to tends to 0, therefore we say that this t of xn going to converge to 0 in n dash as n tending to infinity. Thus for this sequence xn converges to, so this sequence xn converges to, okay, 1 minute. So for this sequence xn converging to 0, we have this t of xn converges to t of 0 that is equal to 0. Thus hence what we get, thus we can say that thus t is continuous at origin. Okay, so this we have proved that 2 if and only if 3. So the last statement is 3 if and only if 4. So I will give the hint. I will show the first part, that is 3 implies 4, and you try the 4 implies 3 by yourself for your homework. So suppose this 3 holds. Okay, so what is 3? That is, there exists a non-negative real number k such that this norm of t of x will be less than or equal to k into norm of x for all x belongs to this n. So this is 2. So what we have to show, that this t of s is bounded in n dash. So what is s? S is nothing but the closed units pair in n. So how we are going to show that? Now for any x belongs to s, what we get, this norm of this x is less than or equal to 1 by definition of s. So this norm of t of x will be less than or equal to k. Okay, since by 2. So how we are going to write, this norm of t of x will be k into norm of x, and norm of x is less than 1. So this norm of t of x will be less than or equal to k, obviously. Hence, so the norm of, so x is member of this s, and this norm of t of x is less than or equal to some non-negative real number. So this s, t of s, so t of x, the members are t of s, so every member of this t of s is bounded. So this t of s is bounded, so we can say that this t of s is bounded. Okay, so this holds, result holds. Now how you are going to show that this 4 implies 3? So you try at yourself, and for the next theorem, that we are going to show the definition of boundedness, and we will discuss some results, some more theorems and examples in next topic. So stay connected. Thank you.